Yeah, it's live.
Yeah. Okay. So, good morning, all. Today we have our speaker Dharm Veer from Chennai Mathematical Institute, and he will be speaking on H polynomials of Hibi rings. So, as always, this is the 45-minute talk, and after that, we will be having 15 minutes for interactions. If you have any question middle of the talks, then you can just put your question on chat box, and we will consider it. After that, you can ask your questions once your talk is over. So Dharamveer now, yeah, it's yours now. You can
Yeah.
start.
Okay. Thank you, Charney, and thank you for inviting me for this webinar. Okay. So the title of the talk is on H polynomials of Hibi rings. So I will state a conjecture, and the conjecture's name is Charney Davis-Stanley conjecture, and we'll prove in this talk we'll prove the conjecture in a very special case. So I'll just state that, and after stating the conjecture I'll tell like in what case we are going to prove it. And the conjecture is originally from geometry. It was due to Charney and Davis in mid 90s. Then Stanley made a commutative algebra version for that conjecture. Okay, so I'll just start defining some things, some stuff to state the conjecture. So throughout the talk, K will always be a field, and let S be a polynomial ring in n variables, and let S be a standard graded polynomial ring. So that means degree of the variables xi is 1 for all I. Then we can write S as summation and direction mind of Sm, where Sm is the mth graded piece of S. Okay, so now for a standard graded K algebra R, we define a series and we call that series Hilbert series, and that is summation n greater than equals to 0, dimension of Rn Tn, where dimension of Rn is the K vector dimension, K vector space dimension of the vector space Rn, and Rn is the nth graded piece of the standard graded K algebra R, and we denote this series Hilbert series by HRT. Okay, so now a proposition about Hilbert series. So let I be a graded S ideal such that crude dimension of S mod I is D. Then there exists a unique polynomial HT such that the Hilbert series of S mod I is HT over 1 minus T to the power D, where D is the dimension of the ring S mod I. Okay, and this numerator of this quotient polynomial HT, we call this the H polynomial of the ring S mod I. Fine. Okay, so from now onwards, like here I have said that the crude dimension of the ring S mod I is D, but from now onwards I'll just say dimension of a ring. So by dimension of a ring I mean crude dimension of the ring. Okay, and let HT is the H polynomial of the ring S mod I. So the conjecture is actually about this H polynomial of a special type of a ring. Okay, so yeah, one more definition before I state the conjecture. Let I be a graded S ideal such that dimension of the ring S mod I is D. Let F be a minimal free resolution of S mod I over S. Then the ring S mod I is Gorenstein if this R. So I mean in my minimal resolution is 0 to FR to FR minus so on to F1 to F0 to S mod I, where this number R, this should be equals to n minus D, where n is the number of variables in my polynomial ring S, and D is the dimension of the ring S mod I, and rank of the free module FR over S should be equals to 1. So S mod I is Gorenstein if R is equals to n minus D, and rank of FR is equals to 1. Yeah, so one more thing that, so if you guys don't know, if somebody doesn't know about minimal free resolution, so here my all these modules FIs are free modules over S, and this and such that this complex is exact complex or a cyclic complex. So the zeroth homology will be S mod I, and all higher homology will be 0. Okay, so I've defined constant. So now we'll state the conjecture. So let S be a standard graded polynomial ring. Sorry.
Yeah, sorry, Dharamveer. Can you
Always,
hello?
yeah,
So, I mean, someone is
yeah.
asking what
Hi,
is minimum tree
yeah.
resolution?
Am I audible?
Say a few words.
Okay.
One person asked what
Yeah,
is
sure,
minimum
sure.
tree resolution? So, can you feel
Okay,
like
so
maybe you can say a few words? Like,
yeah, fine. So just say what is first what is a free resolution. So a free resolution of a okay, so here my module is S mod I over S is a complex of free S modules such that okay, so here this F dot, just a second, a complex of free S modules and hi of this F dot is equals to 0 for I greater than equals to 1, and h0 of this is equals to S mod I. So I'm defining in this particular case only. So this is the definition for free resolution of S mod I over S. And we say that this free resolution is minimal if the okay, so let me just denote these maps by pr minus 1 and c1. The map from fr minus r minus 1 is phi r, fr minus 1 to fr minus 2 phi r minus 1. So if this phi r minus 1 is contained inside the maximal ideal generated by variables.
Dharamveer,
Sorry,
I mean, your
for
voice
minus
is
1
not
or
clear.
yeah.
Your voice is not clear actually. It's breaking.
Oh, okay.
Can you just?
So is it internet connection or so? Now is it audio clear or not?
No, I think some fluctuation is coming. Like it's
Yeah.
not continuous. So it's little bit breaking actually in the middle of this.
Okay.
Can you speak again? I mean, we can
Okay,
try.
then I will try to. Yeah. Okay. Fine. So, okay. So I just define the. Defining the free resolution for this ring S mod I. S. S of my think of this S mod I as a module over S. Then so this complex S module.
Uh,
The complex from 0 to FR to FR.
Dharamveer, your voice is not
Yeah.
coming. I think it may be some
Yes.
internet connection problem or something else. Like, can you
Okay.
fix it
Okay.
somehow?
Just yeah, just give me 2 minutes. I'll mute myself and then
Sure.
I'll,
Yeah.
just a second.
Yeah. Hello, Dharamveer. Hello, Dharamveer. Can you hear me? Are you here?
Okay, so just give me 1 minute. I'm just checking my internet connection.
I
Sorry.
think yeah. So I think maybe you can try just like go out and then again rejoin the
Yeah.
meeting. Maybe it's work. Will work. You can try this.
Okay, just a second.
Uh, Yeah, actually, I'm very sorry for interruption. I think there is some problem in the internet connection from Dharm Veer side. So he just left the meeting and again he's like rejoining. So I'm really sorry. Just wait for a few seconds or just 1 or 2 minutes. Yeah, Dharamveer, can you mute yourself? Can you hear
Yeah.
me?
So am I? Yeah. Am I audible now?
Now it's okay. Yeah, you can start.
Yeah.
Yeah.
Okay.
Yeah.
Yeah. Okay. Just sorry.
Mm.
Okay. So yeah. So I was defining minimal resolution. So I'll just define for this uh, ring S mod I. So think of S mod I as a S module. Now look at this complex. So F dot from 0 to FR to the map, then we have till F0. So all these F5 modules are free S modules, and the homology of this complex is 0 for I greater than equals to 1, and H0 is a S mod I. The zeroth homology is S mod I. And we say that if resolution is minimal, well, in this particular case, if image of all mass phi I, where phi I is mapped from Fi to Fi minus 1, is contained inside the maximal ideal generated by variables x1 to xn. Okay, yeah. So now I'll state the conjecture. So let S be a standard graded polynomial ring. Let I be an ideal of S generated by quadratics. So that means the homogeneous polynomials of degree 2, such that S mod I is Gorenstein. Let HT be the H polynomial of S mod I and degree of HT is R. So assume that R is even. Then minus 1 to the power R over 2, H minus 1 is greater than equals to 0. So this is the statement of the conjecture. So now originally this conjecture is due to Charney Davis. So they stated this conjecture in some geometric setting. So that was about H vectors of some homology pairs. So I'll now state that conjecture in geometric settings, and then Stanley transfer this in commutative algebra case. So in this particular case, so S is standard graded polynomial ring, Ij ideal generated by degree 2 homogeneous polynomials such that S mod I is Gorenstein. If the degree of the H polynomial is even, then this quantity is greater than equals to 0. So Now let R be a ring that satisfies the hypothesis of the conjecture. We say that R is Charney Davis-Stanley, or in short CDS, if the conjecture holds for R. So in 2004, Brandon proved that all Gorenstein Hibi rings are Charney Davis-Stanley, or CDS. So we'll prove a special case that all Gorenstein Hibi rings of regularity 4 are Charney Davis-Stanley. Okay, so now I'll define Hibi ring. So before that, I'll state some lattice theory definitions. So let P be a finite poset. A subset alpha of P is said to be an order ideal if for any x belongs to alpha and y belongs to P, with y is less than or equals to x, we have y belongs to alpha. So in other words, if some element x is in alpha, then all the elements of y, P, those are below x, will also be in alpha, right? Let IP be the set of all order ideals of P. Then under the operation of join, union and intersection, IP forms a distributive lattice. And since P is a finite poset, IP will be a finite distributive lattice. Okay, so one more remark. Throughout my talk, P will always be a finite lattice and a distributive lattice will also be always finite. Okay, so one more definition. Let L be a finite lattice. An element little x in L is called join-irreducible element if x is not the minimal element of L, and whenever x is the join of two elements y and z for some y and z in L, either x is equals to y or x is equals to z. Right? So x should not be minimal element, and we cannot write x as join of two elements where neither of them is equals to x. Okay. Let P be the poset of all join-irreducible elements of L. Okay, so I have defined two things here. So in the first definition, I defined order ideal of a poset. Then I defined the set of all order ideals, and then I stated that set of all order ideals forms a distributive lattice under the operation of union and intersection. And now I've defined join-irreducible element for a finite lattice. Okay, so now I'll state a theorem, and this theorem is due to Birkhoff. So let L be a finite distributive lattice, and let P be the poset of all join-irreducible elements of L. Then L is isomorphic to the order ideal lattice generated by P. Right? And this theorem, so this theorem is actually very important theorem for this talk. Yeah, so from now onwards, if I want to define a distributive lattice, I'll just define a poset first, and then I'll say that let I of P is the distributive lattice corresponding to P. Okay, so now I'll define the Hibi ring. Let L be a distributive lattice with P is equals to P1 to Pn, where P is the poset of join-irreducible elements of L. And since P is finite, so L is also finite. But this is the remark that we have earlier stated, that all my distributive lattice will always be a finite distributive lattice. So let R be a polynomial ring in n plus 1 variables. The variables are t, z1 up to zn. Okay, so for an alpha in L, and note that alpha is actually order ideal of P, so it will be a subset of P. Let U alpha be a monomial of R, is defined by T into my product of Zi if Pi belongs to alpha. If Pi is in alpha, then we are taking product of Zi, all such Zi's. For example, let's consider this. So we have P is equals to this poset. So and now we have P1, P2, and P3. This belongs to I of P. P1, P2, P3 belongs to I of P, right? So the corresponding the monomial corresponding to this will be T times Z1, Z2, Z3. Finding a monomial corresponding to an order ideal. So for alpha in L, U alpha is a monomial, a product of the variables ti and zi, where zi will be there if pi is an alpha. And let RL be the subring of R generated by all such monomials. So all such monomials U alpha for alpha in R. So RL, we call this ring RL is the Hibi ring associated to L. Okay, yeah. Okay, so now we have defined a ring corresponding to a distributive lattice. So now the next task that we want to do is we want to relate the algebraic properties of the ring with the commutatorial properties of the distributive lattice or the poset of join-irreducibles. And the first observation is that dimension of this ring, the plural dimension of this ring RL is equals to cardinality of P plus 1. Okay, so now give an example. Let P be this poset, P1, P2, P3, P4. Let P be this, then the distributive lattice I of P will be here, will be this. So we have the minimal element is the empty set, then we have singleton P1, P2, and join of P1, P2 will be union of P1 and P2, that is P1, P2. And then we have P2, P3, P4, and so on. So the corresponding Hibi ring will be, so corresponding to the variable empty set, sorry, the order ideal empty set, we have variable T. And corresponding to P1, we have TZ1. Corresponding to P2, we have TZ2. Corresponding to P1, P2, P4, the monomial we have is TZ1, Z2, Z4. Okay, yeah. So now let K alpha is a polynomial ring generated by the variables X alpha, where alpha is in L. Okay, so I mean, I'm indexing the variables of the polynomial ring by the elements of the distributive lattice L. So define a map, ring map from KL to RL by X alpha maps to the monomial U alpha. Then the kernel of this map will be a degree 2 polynomial generated by degree 2 polynomials. What are those polynomials? X alpha minus X alpha X beta minus X of alpha join meet beta into X of alpha join beta, where alpha beta belongs to L and alpha beta are incomparable elements of the distributive lattice. That means neither alpha is greater than equals to beta nor beta is greater than equals to alpha. For example, in this particular distributive lattice, I mean the distributive lattice that we have stated in a previous example, our P1 and P2, P4 are two incomparable elements, and P1 and P2 are two incomparable elements. So there will be two generators corresponding to these two incomparable elements. Okay. Yeah. So the kernel of this map, we denote this by IL, and we call this the ideal. Then we will have, so note that this free map is a surjective map because RL is generated by the monomials U alphas, right? So then RL will be isomorphic to KL over IL. So if you remember the statement of the conjecture, so there we had a polynomial ring, standard graded polynomial rings, and the I is should be generated by quadratics. So here my Hibi ideal is generated by degree 2 homogeneous polynomials. Okay. Sorry. Okay, now I'll state some definitions about posets. So let P be a poset. A chain C of P is a totally ordered subset of P, and the length of a chain C is cardinality of C minus 1. Okay, and the rank of a poset P is the maximum of lengths of chains of P. So look at all the chains in P and then look at the maximum of those. And a poset is called pure poset if its all maximal chains have same length. So I'll give an example where what pure actually means. I'll just give an example. And for two elements X and Y in P, we say that Y covers X if Y is greater than X and there is no Z that lies between Y and X. So that means there is no Z in P with the property that y is greater than z is greater than x. Okay. So I'll define a pure poset here. Now a theorem due to Hibi. So Hibi proved in 87 that a Hibi ring R of IP is Gorenstein if and only if P is a pure poset. So this is another property about the algebraic property of the Hibi ring and the commutator property of the poset. Okay, so now for example, look at this poset P1, P2, P3, P4. So
Yeah,
all the
Dharamveer,
chains, yes,
Dharamveer. I mean, someone
yeah,
is asking what is U alpha? U alpha is the product of X alpha and T.
yeah, yeah, right, yeah. U alpha, I've defined it here.
Hmm.
So just a second. U alpha is this. So we given a variable, sorry, given an order ideal alpha of L, we are defining a monomial of R, and it is defined like this. So it is product of T and Zi's, and Zi will be there in the product if Pi belongs to alpha. Okay, so for example, in this particular example, right? So we have P1, P2, and P4 is a order ideal of this poset P. So now the corresponding U alpha for, sorry, so corresponding U alpha for this particular order ideal alpha will be T to Z1, Z2, Z4. So there is no P3 in the order ideal. So there is no P4, Z3 in this particular monomial. So, right? So if order ideal is only P1, then the corresponding monomial is T into Z1.
Yeah.
Yeah, is it clear now?
Yeah, you
Okay.
can go ahead. Yes.
Yeah, sure. Okay. So yeah, Hibi ring is going. I'll define this. Yeah. Okay. So note that the conjecture was about the rings of about S mod I, where S I is generated by quadratics and S mod I is Gorenstein ring. And now by this theorem, we know that S mod the Hibi ring RL will be Gorenstein if and only if the poset P is pure. So now we'll only talk about pure posets. Okay. Yeah. So now one more definition. Let S be a polynomial ring, standard graded polynomial ring. Let I be a graded S ideal. Let F dot be the graded minimal free resolution of S mod I over S. So we defined what is minimal free resolution earlier. So it will be graded if the maps, these maps between the free modules are of degree 0. Let F dot be the graded minimal free resolution of S mod I over S. Then the regularity of S mod I, and we denote this by regularity of S mod I here, is the maximum of J such that beta I plus J is not equals to 0 for some I, where beta Ij is this number here. Right? So it is the maximum of J such that beta I plus J is not equals to 0. Yeah. So now there are two facts. One is that the regularity of the Hibi ring RIP, where P is finite poset, is equals to degree of the H polynomial. Right? And if you note that the H polynomial is actually the numerator of the Hilbert series of the ring R mod RIP. Right? So regulate, okay. And so second fact is that regularity of RIP is equals to cardinality of P minus rank of P minus 1. So this is another property where regularity of a ring is actually algebraic property of a ring. So we have related the algebraic property of the Hibi ring with the commutatorial property of the poset or the distributive lattice. Okay, so here we have, this is we have related it to commutator property of a poset. Okay, so if you remember that we wanted to prove the conjecture for Gorenstein Hibi rings of regularity 4. Right? So let P be a pure poset. So why we are taking pure? Because we want the Hibi ring to be a Gorenstein ring. and let RIP is the Hibi ring associated to IP, such that regularity of IP is equals to 4. Now we want to prove the conjecture for regularity for Gorenstein Hibi rings. So if the regularity of the Hibi ring is 4, then the degree of the H polynomial will also be equals to 4, because this is because of fact 1. In fact 1 we stated that regularity is actually equals to the degree of the H polynomial. Okay, so now one theorem from due to Stanley. So this is actually about the Hilbert polynomial, sorry, H polynomial. So let S be a standard graded polynomial ring. Let I be a graded S ideal such that S mod I is Gorenstein. Let HT be the H polynomial of S mod I. Then HI will be actually equals to H of R I minus H of R minus I, for I where I is between 0 to R. So this is the H polynomial. So that means H of 0 will be equals to H of R, H of 1 will be equals to H of R minus 1, and so on. So by this theorem, we have that in our case where regularity of the Hibi ring is 4, we will have that H0 is equals to H4 and H1 is equals to H3. So we will have this one, this result. So H0 is equals to H4 and H1 is equals to H3. So now one more fact, that this will clarify that how the H polynomial of the regularity for Hibi ring will look like. So H polynomial will be equals to 1 plus Ct plus H2t square plus Ct cube plus t to the power 4, where C is the codimension of the Hibi ring. The codimension will be equals to the embedding dimension, that is the number of variables in the ring KL, minus the dimension of the Hibi ring, that is equals to cardinality of P plus 1. Okay, yeah. So now we know that the case we want to prove, that is like we want to prove the conjecture for Gorenstein Hibi rings of regularity 4. So now we have an idea like how the H polynomial will actually looks like in that particular case. So now we will proceed towards the proof of this. So now before that, one definition, let P be a poset. P is called simple if there is no element little p in P with the property that all elements of P are comparable to P. Okay, so there is, okay, so for example, if we consider this particular poset, we have P3. So note that every element of the poset is actually related to P3. Either it is above P3 or it is below P3. Or sorry, either it is greater than equals to P3 or less than equals to P3. But in this particular case, there is no element in the poset that is comparable to every element of the poset. So this is a simple poset. So in the next theorem, okay, so not next theorem. So in this particular observation, so let P be a non-simple poset. Okay, so that means there are some elements in P, those are comparable to every element of the poset. And let P prime be the subset of all those elements, those are comparable to every element of P. And now look at the subposet P double prime, that is P minus P prime, and note that P double prime will be a simple poset, because we have removed all the elements in P. I mean P double prime is obtained by removing all the elements from P, those are comparable to every element of P. Okay, so now one fact, that in that particular case, the Hibi ring associated to P will be isomorphic to the Hibi ring associated to P double prime tensor over K with the polynomial ring in R variables, where R is the cardinality of the poset P double prime, sorry, P prime. That means there are R elements in the poset P, those are comparable to every element of the poset. Okay, yeah. So one more fact. Okay, so one more fact. So in this case, let's say HT is the H polynomial of RIP, and H double prime T is the H polynomial of RIP double prime, and H prime of T is the H polynomial for this polynomial ring. Then since I mean R of IP is the tensor product of these polynomial rings, then in that case my H polynomial will be product. So HT will be a product of H double prime T and H prime T. But the second ring, that is so this is a polynomial ring ky1 to yr. So in that case, H prime T will be actually equals to 1. The Hilbert series will be 1 over 1 minus 2 to the power r, where r is the number of variables that we have. So HT is actually equals to H double prime T, right? So if we want to prove the conjecture for a non-simple poset, then it is enough to prove the conjecture for the poset P double prime, where P double prime we obtain from by removing all the elements of the poset. Those are comparable with every element of P. Okay, so in other words, now it is enough to prove the conjecture for simple posets. So it is enough to prove the conjecture for simple posets. Okay, so let P be pure poset. So why we are taking pure? Because in that case, my Hibi ring is Gorenstein ring. And let regularity of RIP is equals to 4. Okay, so if the rank of the poset is 0, then in that case, so we know that by one of the fact that regularity of RIP is equals to rank cardinality of P minus rank of P minus 1. So if the rank is 0, then cardinality of P will be actually equals to 5. So in that case, P will look like this. So P is an anti-chain of 5 elements. Then, so we can compute the H polynomial for this directly, and H polynomial will be this. So in that case, so we can see that H of minus 1 is greater than equals to 0. Hence the conjecture hold for this. Right? So now it is enough to assume that P is a simple poset of rank greater than equals to 1. Okay. So now, yeah, so I'll define something here. So let P1 and P2 be two posets. Define a poset on the set P, define a poset P on the set P1 union P2 with the following order. If x comma y belongs to P, then x is less than equals to y in P if either both x and y belongs to P1 and x is less than y in P1, or both x and y belongs to P2 and x is less than equals to y in P2, or x belongs to P1 and y belongs to P2. Right? In other words, in my poset P, every element of P1 will be less than equals to every element of P2. Okay, so now how the Hesse diagram of the poset P will looks like in that particular case. Yeah, so here is the example. Let P1 is this poset and let P2 be this poset. So then how poset P will looks like? So we will have a poset, we have P1 here, right? And at top we have the poset P2, right? And now the condition 3 forces, here, that every element of P1 is less than equals to every element of P2. So in other words, if it is enough to make the relation between the maximal elements of P1, we have maximal elements are here P3 and P4, and minimal elements of the poset P2. So there is an edge between all the maximal elements of P2, so P1 with to all the minimal elements of P2. Sorry, let me just clarify it. So not that there is an edge from P3 to P6 and P3 to P5. So P3 is the maximal element of P1 and P5 and P6 are the minimal elements of P2. And there is edge between the maximal element P4 to all the minimal elements of P2. So yeah, so this is how my P will looks like. And this is actually very important. So the way for defining the poset P is actually very important for the proof of the conjecture in our case. Okay. So now a lemma, let P1 and P2 be as above. Suppose that P is a pure simple poset of regularity 4, right? So what does P1, P2 and PR as above means? So we have two poset P1 and P2, and P is obtained from P1 and P2 in by this particular definition. Okay. And suppose that P is pure simple poset of regularity 4. Then the Hibi ring associated to P will be Charney Davis-Stanley. Okay. Yeah. So before we proceed to the proof of this lemma, so there is one observation or fact. So if P1, P2, P3 are as above, then R of IP is isomorphic to the tensor product of these rings are the Hibi ring corresponding to P1 and P2 modulo a relation. So now what is this relation? Okay, so note that P1 is a order ideal. P1 belongs to I of P1. That means P1 is a order ideal of I of P1. Sorry, P1 is actually order ideal of P1, right? And empty set will be order ideal of I of P2. Yeah, right. Okay. So now in the so now let xp1 is the variable corresponding to sorry. So let me just rewrite this statement. Sorry, just give me a minute. So let k x alpha alpha belongs to I of P1 tensor with just a second, sorry. So modulo I of IP1. So I of IP1 is the Hibi ideal for the ring RIP1 tensor with K y alpha, where alpha belongs to I of P2 modulo I of IP2. So this is the Hibi ring associated. This is RP1 and this is RIP2, right? So we are taking tensor product of these Hibi rings, and we are now identifying two variables of these. So xp1 minus y phi. Right. So here xp1 is the variable corresponding to the order ideal P1 of IP1, and y empty set is the variable corresponding to the empty set of the that is the order ideal of IP2. So RIP is actually equals to tensor product of the Hibi rings of IP1 and P2 modulo 1 relation. Now let HT be the H polynomial of RIP and HIT be the H polynomial of RIPI. Then HT will be actually equals to product of these product of H polynomials of H1T and H2T. Okay, so now we'll use this observation or this fact in the proof of lemma 1. Okay. So case 1, either degree of H1T, so not that degree of HT is equals to 4, because we are in the regularity 4 case, where regularity of the Hibi ring is 4. So either degree of H1T is equals to 3 or degree of H2T is equals to 3. So consider this particular case. Then by the Stanley's theorem, and that theorem states that Hi is equals to Hr minus I. We will have that Hi of minus 1 will be equals to 0 for I is equals to 1 and 2. And hence for the product we will have H of minus 1 is equals to 0. Hence the conjecture holds in this particular case. And if the degree of HIT is equals to 2, then so we have stated drawn all the possible poset, pure poset, simple posets with of regularity 2. So, sorry, in those case regularity of the Hibi ring is equals to 2. So there are 4 possible cases. So when the rank of the poset is 0, we have this, and if the rank of poset is equals to 1, then we will have all these three possibilities. So one can observe that hi of -1 is less than or equals to 0. So I have written the h polynomial for each of the posets. So h of I of -1 is equals to is less than or equals to 0. Hence h of -1 is greater than or equals to 0. Right? So the conjecture is true in this particular case. So now one case is left here, that is when degree of one of the hi is equals to 4 and the other of hi is equals to 0. But that case will not happen, and the reason is that we are taking P to be a simple poset of regularity 4. So that case will not occur. Okay, so this is the proof of the lemma 1. Okay, so now before stating the next lemma, so let me define something. Let P be a pure poset. Q0 be the set of all minimal elements of P. And Q1 is the set of all elements of P that covers any element of Q0. That means Q1 is the set of all elements P in P, so that P covers Q for some Q belongs to Q0. So let me just define what covers means again. So Y covers X if Y is greater than X and there is no Z belongs to P with Y greater than Z greater than X. So we defined this earlier. So that means Q1 is the set of all elements, those covers some minimal element. Okay, so now I'll state lemma 2. Let P be a simple pure poset such that regularity of RIP is equals to 4. Let P prime be a pure poset. Let P prime be a pure poset obtained from P by omitting an edge between Q0 and Q1. So I've defined Q0 and Q1. Q0 is the set of minimal elements and Q1 is the set of those elements, those cover some element of Q0. Let P prime be a poset obtained from P by omitting an edge between Q0 and Q1. So if RIP is Charney Davis-Stanley, then so is RIP prime. Okay, so we will not prove this lemma, but now using lemma 1 and lemma 2, we have the proof of conjecture. Okay, I'll state how. So for example, let's consider this particular poset P. Note that cardinality of P is equals to 7 and rank of P is equals to 2. Hence, regularity of RIP equals to 4. 7 minus 2 minus 1. Okay. So now how will proceed to the proof of this one? So consider this poset P0. So note how we obtain P0 from P. One second. Okay. So from here onwards, P0 and P are same, right? But between Q0, I mean between the minimal elements and the Q1, I have added all possible relations. That means every element at here is above all the minimal elements. And at this, so this is also above all the minimal elements. So by lemma 1, R of IP0 is CDS, because we can think of it as, so consider, so let's say this is my poset P1 and this is my poset P2. Then P0 is defined on P1 union P2 by the condition that every element of P2 is greater than or equals to every element of P1. Right, and in lemma 1 we prove that in that case my Hibi ring is CDS. Okay, so now I'll use lemma 2. I have removed this particular edge. So this edge here. So I have removed this particular edge from P0. So by lemma 2 we know that R of IP1 is Charney Davis-Stanley, because R of IP0 is Charney Davis-Stanley, right? And in the next part, so I have removed this particular edge. And then again by lemma 2 R of I. So, and this is actually the poset P. So then by lemma 2 R of IP is Charney Davis-Stanley. Right. So once again, so P is this poset I have. So I have formed a poset P0 using P by adding all the possible relations between level 0 and level 1. By lemma 1, we know that R of IP0 is CDS. And then we use lemma 2 by removing one edge at a time to obtain P. And by lemma 2, we know that all RPIs will be actually Charney Davis-Stanley in this particular process. And that's it from my side. Yeah, that's it. So any questions?
Yeah, Bisal Dev, you can ask your question. Yeah, unmute yourself and you can ask.
Hi. So my question is, so I've noticed that the Hilbert polynomial for the anti-chain with 5 elements, that's 120. The coefficients are 126, 66, 26, 1. And for 3 elements, that's 141. So these are the Eulerian numbers corresponding to
Eulerian polynomial
S5 and S3. So
can
you tell me what's the connection?
Yeah, I mean, it's the precise. So let's say P is a chain, anti-chain of n elements, P1 to Pn. Then the corresponding H polynomial will be actually the Eulerian polynomial. Nth Eulerian, so I think we call this that nth Eulerian polynomial.
Okay.
Yeah. So corresponding to a anti-chain, the H polynomial is actually the Eulerian polynomial.
Okay. So is it easy to see the proof of this?
Well, okay. So actually, the proof is more general, and so this is how we actually prove the lemma 2, that the proof of which I have not stated. Okay. So let me just state it. So let P be a poset naturally ordered. So, okay, so let me just write it, sorry, here. Let P is naturally ordered. P greater than equals to is naturally ordered. That means if P is less than equals to Q in P, then, okay, so P is a poset on the set of n natural numbers 1 to n on the set n, and P is naturally ordered if P is less than equals to Q in P, then P is less than equals to Q in n, in the set of natural numbers.
So this is a linear extension.
And in that case,
so the natural order is a linear extension on this poset.
Yeah, right. Okay. Yeah, right. So then in that case, my h of t will be actually equals to the linear extensions, h of phi of t. Yeah, so this is a theorem due to Hibi. So, or in particular, if my P is a anti-chain, in that case, so this function, the function of linear extension is actually the Eulerian polynomial.
So how do you define this function, WPT?
Okay, so yeah, just a second. Okay, so just a second. Okay, so now so this is WPT is summation where pi belongs to, okay, so L of P, where L of P denote the set of all linear extensions, T to the power descent of pi. So pi, yeah, so look at the descents in the pi and then we count so this is function.
Okay, so descent is defined in the usual way, like
yeah, right. So pi of I is greater than equals to pi of I plus 1. So there is a descent at ith position. right? And then in some particular permutation, if there are so with descent of W, descent of pi is the number of descent in the permutation pi.
Okay.
In pi.
Okay.
Yeah. So then this count this. Yeah. So this is how it defines. So in like if P is an anti-chain, in that case the WPT is actually equals to irreducible polynomial.
Right. I see. Okay. Yeah. Thank you. And another question is there some way to compute these polynomials that, like, if I'm given the Hasse diagram of a poset, is there some way I can directly compute h of t without having to go to the
actually is so. And so, okay, so for rank 0 poset, it is a G, right? But in general, I mean, this is, so it is not that easy to compute, or I don't know any way to compute this. Even so we use this particular approach for proving for regularity for case, but in Brandon's case, he used some different theory. So he defined something called sign graded posets, and using those particular posets, he proved the conjecture for Gorenstein Hibi ring case. But I mean, to computing the descent polynomial or this WPT for any poset, we don't know. Like, is there any way, easier way out? Yeah. So I tried it, but like it seems very difficult.
Okay. And another question is, you have this quantity that is non-negative, and it's also an integer. Is there a combinatorial interpretation of this? So h of minus one power, I think r over 2.
Yeah, right.
So is there a combinatorial interpretation related to some quantity in the poset?
No. So like we are only interested. No, we are only interested in the sign of this number.
Yes.
So like any commutator for this number, we don't know. So in the conjecture, we are only interested in the sign of this particular thing, right?
Right.
So yeah, so I don't know that whether so if there is any commutator interpretation for this number or not.
Okay. Thank you.
Yeah.
Is there any other question?
Actually, I have one question. Hi, Dharm.
Yeah.
Yes. You have defined the regularity for the Hibi, possibly for the when you have given the map and then you have find the quotient, no? So
right.
So no, but here the generator are in different degree. So do you have used a standard grading or something else?
Okay,
because T is in different.
I have, so for when I did, so yeah, so I have taken the standard graded. Okay, and I am taking graded idea here.
Sorry.
So in the definition, so my S is a standard graded polynomial ring I'm taking.
Yes. Right? Yes.
And I'm taking to be a graded S ideal. And then I'm computing the graded minimal free resolution.
Yeah.
Right.
This definition is fine. Here it is, everything is standard. But when you go to the Hibi ring, when you go to the Hibi ring, then the generator of the rings are not the standard.
Yes, I mean then the Hibi is generated by degree 2 is generated by degree 2 homogeneous polynomials only. So sorry, I'm not following your question.
No, okay. Can you come to the Hibi ring definition? Just
okay, sure. So yeah, I've defined the Hibi ring here. So this is
okay. Let me say something. Like here, your KL is a
polynomial
X alpha also.
Yeah.
Now kernel is X alpha X beta minus X alpha intersection beta join and meet.
Right.
So now this is ring is isomorphic to R over L, R of L.
Yeah, right. Yeah, right.
But
Right.
my doubt is about the you are considering a Hibi ring as a R of L or KL of mod I, because in the R
so
model,
yeah, so
the generators are not in the standard grading.
yeah, okay, yeah, fine. So whenever I was like saying that let S, so I was defining everything for a polynomial ring, right?
Okay.
In conjecture, I've defined it for like S is a polynomial ring and I is the ideal generated by degree 2. I is ideal generated by quadratics, right?
Okay.
So in that setting, so I was writing RL at every case, but I actually mean that I'm actually considering Hibi ring as KL over the Hibi ideal.
Fine.
Okay. So I was just noting it by RL or R of IP, but I actually mean it like this. Yeah.
Okay. One this conjecture you have proved for the regularity 4.
Yeah,
is it
regularity
open
4
for other regularity or it is proved?
No. So in general, for Hibi rings, it is proved. It is proven by Brandon.
Okay.
And in 2004, he proved that all Gorenstein Hibi rings are Charney Davis-Stanley. But in general, the conjecture is still open. Like if I take any polynomial ring and any ideal I generated by quadratics, such as S mod I is Gorenstein, so it is open in general.
Okay.
But for Gorenstein Hibi ring case, this is already proven. Yeah.
Okay. Thank you.
Yeah.
Is there any other question? If not, then let's unmute yourself and thanks speaker by clapping. Thank you, Dharm Veer.
Thank you.
So we'll be meeting on next week again, the same time, Wednesday, 11 same time, and our next speaker will be Nonat from CMI Chennai. Again. So,
yeah, and sorry regarding the disturbance in the beginning of the talk. Like that was
that's okay.
So yeah.
So, thank you, Dharm Veer, again, and I think
thank you.
We are done. Okay.
Thank you. Yeah. Okay. So regarding Euler polynomial. Yeah. Okay. So there is a paper of Rayner and Walker. Okay. So that is, I think, on Charney Davis conjecture and Stanley Nigger conjecture. Just a second. Let me. Yeah. So the title is on the Charney Davis and Nigger Stanley conjectures. Rayner and Walker.
Okay.
Victor Rayner and Walker.
Okay.
Yeah. So.
And so that has like Hilbert polynomials and all of that as well.
Well, no. So I think he's done this in. So Hilbert polynomial, he did not define it like this. Yeah, he did not define it like this. No. Okay. So yeah, you can find Hilbert polynomial.
Okay.
Yes.
Okay. And, is it also there in?
Yeah. Okay.
Is it also there in Stanley's book, Combinatorics and Commutative Algebra?
I don't think so.
Okay.
I think I think it is not there.
Okay.
But I just have a look, but I don't think it is there.
Okay. Thank you.
Okay. Yeah.
And about this, so this conjecture and everything, it's there in this paper by.
Yeah. Right. Yeah.
Thank you.
Yeah. So is there any questions? Okay, Samir, I'm logging off then. Yeah, thank you.